Hello students, now we will study electrostatic potential due to a system of charges.
So we consider a system of charges. We are having many number of charges. Say in the diagram we have shown, you have taken only 5 charges, Q1, Q2, Q3, Q4 and Q5, and in the similar way we can take small n number of charges which are kept at a distance. Q1 is at a distance from point P is R1P, Q2 is at a distance R2P, Q3 is at a distance R3P, Q4 at R4P, Q5 at R5P, and so on. So we have taken a system of charges. Say these charges are given as Q1, Q2, Q3, Q4, Q5, and similar way we can take up to n number of charges Qn, and their position vector are given as R1P, R2P. Position vector means the distance of these charges from the point P we have taken. So this is R3P, and maybe this will be taken as RNP. So we want to calculate the potential at point P due to the system of charges. So in order to calculate the total potential, we have to take these charges one by one, and then we have to go through the total electrostatic potential. So let us start with the first charge. So the potential V1 at point P due to the charge Q1, the electrostatic potential V1 due to charge Q1 is given as V1 is equal to Q1 upon 4 pi epsilon naught R1P. Similarly, if we want to calculate due to charge Q2, it will be given as Q2 upon 4 pi epsilon naught R2P. And due to other charges in a similar way, we can calculate V3, V4 and so on up to the nth number of charge. We can go like this because we know the formula of electrostatic potential, so we can easily write it down. So here you can see in all these expressions, R1P is the distance of charge Q1 from point P, R2P is the distance of charge Q2 from point P, this is the distance of charge Q3 from point P. So these are the position vectors of these respective charges. And so once we have done with the electrostatic potential due to all these number of charges, then we can simply use the principle of superposition. We can apply this principle to calculate the total electrostatic potential at point P due to these n number of charges. So the principle we are applying is the principle of superposition. So now apply this principle and we get the total electrostatic potential as a sum of all these potential due to n number of charges up to Vn. Right? So what we can say that by the superposition principle, the potential capital V, the total electrostatic potential at point P due to the total charge configuration is the algebraic sum of potential due to individual charges. Here we have taken the algebraic sum, we are adding these individual potential, and we will have the total electrostatic potential. Now simply putting the value we have 1 upon 4 pi epsilon naught. Inside the bracket we'll have Q1 upon R1P plus Q2 upon R2P plus Q3 upon R3P, and so on up to nth. This is Qn upon Rnp. So this is the total electrostatic potential. So if it is known to you, you can simply add them up. Now we will consider this as a total electrostatic potential V. So next move on to the points to remember. So the points we have to remember if we are taking a number of charges. The first point we have to remember is that if there is a continuous charge distribution, instead of having these individual charges Q1, Q2, Q3 and say up to Qn, if we are not having this type of charge configuration, but we are having a continuous charge distribution. That means we are not having discrete charges, but we are having a uniform charge or continuous charge distribution. Then how we can write down the total electrostatic potential? Because if there is a continuous charge distribution, we can take the volume charge density rho. This is the rho is the volume charge density, and it is a function of the distance r. So I've written rho as a function of r. So we divide this charge distribution into small volume elements. Delta V can divide all these into small volume elements, say delta V1, delta V2, and so on up to delta Vn. These are the small volume elements, and then the charge Q will become this volume charge density multiplied with the volume element rho delta V, and we can determine the potential due to each volume element, and then we can calculate the total by summing over each contribution. We can calculate all these small contributions and we can sum them up, and then we will have the total electrostatic potential V. Second point is that if we are having a uniformly charged spherical shell, we are taking a uniformly charged spherical shell. That means the charge is uniformly distributed over a spherical shell. What is a spherical shell? That if you take a sphere and it is not solid, it is hollow from the inside, then you have the two radius, inner radius and the outer radius, and then we call it a spherical shell. And we know that inside the spherical shell, the electric field is zero, and outside the spherical shell, the electric field behaves as if the entire charge is concentrated at the center. If you want to go to this derivation, I have given link below of this lecture. I have given you the link for the application of Gauss law, where we have calculated the electric field due to a spherical shell. But as for now, you can simply say that the electric field outside the shell simply behaves as if the total charge is concentrated at the center of the spherical shell. So we can write down the potential using this simple concept, that the potential outside the shell. We know the electric field outside the shell. So the potential outside the shell is given as capital V is equal to Q upon 4 pi epsilon naught R. Here this R is very greater than this R. Okay, the distance we have taken at the point where we are calculating the electrostatic potential is very greater than the radius of the spherical shell. That means this point is somewhere outside the spherical shell. Third point is that the electric field is inside the shell is zero. If we are taking a uniformly charged spherical shell, then the electric field inside the spherical shell, we have derived it, and if you want to go to the details, I have given you the link. So inside the spherical shell is zero. It is zero. So what will be the electrostatic potential? So the electrostatic potential is constant inside the spherical shell. Now, how come it is constant? It is constant because if you go inside the spherical shell and if you continue moving the test charge, then no work is done in moving a charge inside the shell. Inside the shell, electric field is zero, that means the electric force is zero, and if the force is zero, that means the work done will be zero. So if inside the shell the work done is zero, that means whatever is the value of electrostatic potential, it will not vary, it will not change, and the electrostatic potential will remain constant and it will be equal to its value at the surface. So whatever is the value of electrostatic potential is at the surface of the spherical shell. Whatever is here, as you move inside, it will remain same. So the electrostatic potential is constant, and we can write down the value at the surface as Q upon 4 pi epsilon naught R. So if this is the value of electrostatic potential at the surface, it will remain same throughout. As we move inside the spherical shell, the value does not change, it remains same. The electrostatic potential is constant because the work done is zero, no electric field is working, no electric force is working. So the value remains the constant. So for the spherical shell, this is for the outside and this is for the inside. And if you're having a continuous charge distribution, you can use this formula. So considering these 3 points, we can calculate our electrostatic potential in each case. Equipotential surface. Surface with equal potential. So we define a surface. So if we define a surface which has constant value of potential at all points of the surface, then we call this surface as equipotential surface. Or in other words, any surface which has equal electrostatic potential at any point is called an equipotential surface. If we have a point charge small q, then the potential is given by the expression capital V, and we have just derived the formula for capital V is equal to kq upon r, or in other words 1 upon 4 pi epsilon naught q upon r. So this is the formula for the electrostatic potential due to any point charge q. So if we look at the formula, then this 1 upon 4 pi epsilon naught is equal to k, which is already a constant. And if we are taking any point charge, then q is also constant. So v is a function of r only. So v depends on the value of r. If this r is kept constant, that means in turn we will have this v as a constant. So there is a simple physics behind this, that if r is constant, then v will also be constant. So if we are having any point charge q, which is a positive charge, then using this positive charge plus q at equal distance small r, we can draw an equipotential surface. This is our point charge plus q. Then at any distance small r, we have drawn this sphere which shows a equipotential surface. If we increase the value of r, we move to the second equipotential surface, similarly to the third equipotential surface or to the fourth equipotential surface. In this way, we can draw a series of equipotential surfaces. So what we see, that the equipotential surfaces of a single point charge plus q are concentric spherical surfaces. If you see from this diagram, the center of all these spheres is same. So we have drawn many spheres with a constant value of r. Say this is sphere 1, sphere 2, 3, 4 and so on. So this sphere 1 has a constant value of r. If we come to 2, then it may have some different value of r, but that is constant for sphere 2. Then for the third sphere, different value of r, but it is constant for the sphere 3. So we can draw many spheres which are concentric, and these spheres will work as an equipotential surface for the test charge plus q. So what we conclude, that the equipotential surfaces of a single point charge are concentric spherical surfaces center at the charge. So these are different spherical surfaces, and whose center is our charge plus q. So the electric field lines, if you want to know what are electric field lines, Then the link for the lecture is given below. You can go through that link and you can find out what electric field lines are. But as for now, the electric field lines for a point charge Q are radial lines. If we have plus Q or minus Q, the electric field lines are always in the radial direction, as we have studied. So always these are in the radial direction, so we call them as the radial lines. If it is a plus Q, then these are moving away from it, and if they are minus Q, then they are moving towards the center. So the electric field lines for a point charge Q are always radial lines, which may be starting or which may be ending at a charge. So the electric field at every point is normal to the equipotential surface. How? Say this is our charge plus Q, this is kept at the center. Then we want to draw an equipotential surfaces. Say a single surface we want to draw, then this is any equipotential surface. Then I have drawn any equipotential surface. This may not be a perfect sphere because I am drawing through my hand. So if this is a charge plus Q, then this is the equipotential surface, which is a spherical surface. So this shows the equipotential surface. And if we draw the electric field lines, then these electric field lines are always in the radial direction. So here I am showing you some of the radial lines which are representing the electric field due to this charge plus Q, and they will always be directed away from the plus Q as our thumb rule. So it will act as a source. So these are the electric field lines. I am representing with the arrow, and this is the equipotential surfaces. So this is our equipotential surface, and these are our electric field lines. So you can see that these two are perpendicular. This is the equipotential surface and these are the electric field lines. So the electric field lines and equipotential surface are normal. So what we can say that the electric field E due to any point charge Q. So what we can say that the electric field at every point due to a charge Q is normal to the equipotential surface passing through that point. So as a result, we can make it a note that for any charge, so what we conclude that for any charge configuration, the equipotential surface through a point is normal to the electric field at that point. This is the simple physics behind the equipotential surface and the electric field lines. We know what are electric field lines, we know the direction of electric field line. So if you are given with any charge plus Q, you can easily draw an equipotential surface, you can easily draw the electric field lines, and simply by this diagram, if the concept is clear in your mind, you can simply say that at every point these electric field and the equipotential surface are normal to each other, and this is true for any of the charge configuration. Now what happens if the field is not normal? If the field we are talking about, the electric field, is not normal to the equipotential surface, it is not normal to our equipotential surface. What happens in that case? That we want to find out. So let us find out what happens then. Then it will have some component along the surface. If the electric field is not exactly normal to the equipotential surface, then it will obviously have some component along the surface. And then to move a unit test charge against the direction of component of field, work is to be done. Are you getting the thing? That if it is not normal, then it may have some component along the surface, and to move any of the unit test charge against the direction of component of field, the work is to be done. And if the work is to be done, then it is not an equipotential surface. The potential will vary, because the potential, where from we get the potential? We get the potential from the work done. And if there is work done, there is some change in the potential. And if there is no work done, then we have the same potential as equipotential. Hope the physics is very much clear to you. So now in an equipotential surface, any 2 points are at same potential. If we come to the word equipotential, it is very much clear from the word itself. Equi is for equal and potential means here the electrostatic potential. So if we are considering any 2 points which are on the equipotential surface, that means at those 2 points the electrostatic potential is equal. So any 2 points are at the same potential and no work is required to move the discharge. No work is required. So whenever we are moving any test charge on equipotential surface, the potential remains the same and no work is required. So what we conclude from all this theory, that the electric field, which is denoted with the symbol capital E and which is a vector quantity, that the electric field E must be normal to the equipotential surface. Make it as a thumb rule that whenever you are having it equipotential surface, the electric field is always normal to the equipotential surfaces. Fine. So now we want to draw certain pictures for equipotential surfaces, and these are very easy to draw. So we want to draw equipotential surfaces. Let us see how we can draw these equipotential surface. Let's quickly move on. So here we have shown some. So here we see some equipotential surface. If there are continuous electric field lines like we have shown here with the red color, these arrowed lines show the electric field line. So this is the direction of electric field, and if the electric field lines are shown in this way, then what will be the equipotential surface? Equipotential surfaces are simply drawn with this pink color, as you can see. So at each point the electric field is same. You can see that if you take any point, then the electric field is same and the potential is also same. So we call this as equipotential surface. So along these electric field lines, we can draw such equipotential surfaces as we have seen in the diagram, as I've shown you that these are few of the equipotential surfaces for the electric field lines which are flowing. So all these squares we have shown, all this frame-like structure, you can see they show the equipotential surface. And if we come to here, you can see a dipole. This is a dipole because we have one positive charge and one negative charge, and we take them equal in magnitude. So here we have shown with a minus charge, and here you can see that this is a plus charge. So for a minus charge, we can draw many equipotential surfaces in form of the concentric spheres. As a similar way, we have shown it for the positive charge. You can see that there is a series of concentric spheres. So here for the minus charge, we have a number of concentric spheres, and for the plus charge, we have a number of concentric spheres. So if we take any of these spherical structure, that each point of any of this sphere, it is having the same value of electrostatic potential. Here if you take this sphere, then at each point of the sphere the electrostatic potential is same. So this series of concentric spheres shows equipotential surface for a negative charge, and similarly here for a positive charge we can draw a number of concentric spheres, and for each sphere which is situated at a distance constant from the center of this positive charge, it is the equipotential surface. So this is how we can draw an equipotential surface for a dipole. And here we have taken two similar charges. these are both are positive charge. You may take them as negative also. It doesn't matter, because as we see here that the equipotential surface will be concentric spheres for both negative as well as positive. So for example, here we have taken two positive charges, so we can see that there are concentric spheres and these two are quite close, you can see. So these concentric spheres, they coincide with the equipotential surface of the second charge. You can see this outermost sphere, then they coincide with each other at this point in this area, you can see. So there is a combined equal electrostatic potential surface. So there is a combined equipotential surface for these two, as we have drawn in the outer structure. So at each point you can take either this point, you may take this point, or you may take this point over here or this point over here. The potential is same here. If you go to these points, then you come to the equipotential surface of the charge, second positive charge, and here you on these points you can see I'm drawing with this green. These are the equipotential surface for the first positive charge, and here, which is a common between these two charges, this is again equipotential surface, because here they coincide with each other. So from this diagram it is very much clear how equipotential surface behaves. Electric field and electrostatic potential. So to find out the relation between the electric field E and the electrostatic potential V, we are just doing a simple derivation, and for this derivation we are taking equipotential surfaces. So we have taken one equipotential surface, that is a surface A. So this is our surface A, it is an equipotential surface and it is kept at a constant potential V. And there is another equipotential surface. This surface we call as the surface B. The surface B is again equipotential surface. That means on any point of the surface B, the electrostatic potential is same. So let us say that at equipotential surface A, the potential is V, and at the equipotential surface B, the electrostatic potential is V plus delta V. That is, slightly amount of potential is added to this. So this is V plus delta V and this is V. And we have taken any point on the surface B, and this point we are calling as P, and this point P is at a distance delta L from the potential surface, equipotential surface A. So we have two surfaces, both are equipotential, a point P on B surface, and the distance between A and B is delta L. And the direction of electric field is shown in the upward direction. So now quickly move to how we derive the relation, which is a very important relation throughout your physics. Whenever you are studying electrostatic, this relation you will use everywhere, and it is very interesting to remember. But let us first derive and then we'll remember it for a lifetime. So let us say that this is V and this is delta V. So what is delta V here? So delta V is equal to a small change in the electrostatic potential in the direction of electric field, because as you are moving up, the electrostatic potential is increasing by the amount delta V. So this is the direction of electric field in the upward direction. So we can say that delta V is the change in V, that is a small change in the electrostatic potential in the direction of electric field, that is in the direction of capital E. So that is how we have defined delta V. Now P is any point on the surface B and delta is the distance between A and P. So now what we do, we take a unit positive charge. We are taking a test charge Q, and this we are taking as a unit positive charge, and we move this charge from potential surface, equipotential surface A to surface B. Okay, we move this charge from A to B in the direction of AP. Right? So if we are moving it from here to here, that means we are doing some work. So how we can calculate the work done? Because there is a change in the potential energy, that means we are doing some work. So work done will be equal to the electric field into dl. Work done is equal to E dot delta L. And this work done, where this work done will go? This work done will add to the electrostatic potential. So this work done will be equal to this should be equal to the potential difference. Because if the potential is increasing, that means that is increasing by the same amount which we are doing the work. So this work adds to the potential difference. So we equate these two. E dot delta L is equal to potential difference. The final potential is V plus delta V and the initial potential is V. So we can take it as V minus V plus delta V. So this is equal to minus delta V. So from this equation we get the electric field E is equal to minus delta V upon delta L. Or if we write down the magnitude of the electric field E, it comes out to be minus delta V upon delta L. And the magnitude will be delta V upon delta L. Fine. So how we can calculate? E is equal to minus dV upon dl. That is the relation we have to remember throughout. We have just derived with this relation, and this relation, whenever you are dealing with the electrostatic or you are dealing with the electric field, it's a lifelong remembrance. It should be always on your tips, that E is equal to minus dV upon dl, or V is equal to minus integration E dot dl. So these two relations we should always remember. Now what we conclude from this? We easily conclude 2 points. First point is that the electric field is in the direction where the potential V decreases steepest. So because it is in the negative direction, so the electric field will be in the direction where the potential V decreases steepest. That means it is having the highest value of del V over del L. So what we can say, that the direction of E is where delta V upon delta L, or the potential decreases at steepest. Now the second point also we can write down is that the electric field magnitude, if you go here, then the electric field magnitude is the change of magnitude of potential per unit displacement, because this is delta V upon delta L. So what we call this? Change in the magnitude of potential per unit displacement. The direction is normal, so normal to the equipotential surface at that point. So electric field magnitude is the change in the magnitude of potential per unit displacement normal to the equipotential surface at that point. So that shows about the magnitude of electric field. Electrostatic potential. If you like, please like and share and subscribe to our channel Physics Class. Thank you.